Recording in progress.
All right, I see you all made it. So here we are online today. So we're going to pick it up where we left off on Tuesday. So I think what we're going to do here is I'm going to save the Excel until we get back when we're all together in the same place. So today we'll just be using the calculators again. And then when we're done with chapter 6, we'll probably have a little time to maybe start chapter 7. And then, of course, we have a complete week off. When we get back, we have to start making plans for a second midterm, believe it or not, because um, we're zooming through the material, and the second midterm is based on chapters 4 and 5 only. So since we've already finished those, when we get back, we'll start to talk about reviewing and then actually scheduling the second midterm. So also the midterms you just took, they should be ready by later tonight, I think. And so I'll make the effort to put the Blackboard gradebook together so that you can see how you did without having to wait until a week from Tuesday. Well, anyway, so what are we going to do in the meantime? So let's go back to our discussion about the normal distribution. And so uh, here we go. All right, so here's the normal distribution. And, we really pretty much covered the main properties of the normal distribution. But let me just quickly run through them again with you. So you have the curve itself looks like this. And of course, as you recall, it has a mean and a standard deviation. The mean tells us where it's located, and the standard deviation tells us how spread out it is. Okay, so we know that because it's a probability distribution, the area under the curve equals 1. Just and what you're seeing me write on here, I'll be posting it in Blackboard so it doesn't get lost. In other words, you don't have to write every single word down because I will be posting this. So area under the curve equals 1. And the distribution is symmetrical about the mean, as you can plainly see. And that can help us simplify some of our calculations. As we saw in the class, areas in the right tail match up with areas in the left tail. So it's symmetrical about the mean. Of course, it's continuous, meaning that there's an infinite number of possible values for the normal distribution. And it is uniquely characterized by the mean and standard deviation. All right, so now what we spent most of our time doing the other day was calculating probabilities. So, oh, one more thing, I want to throw this in here as well. The standard normal distribution is the one that has a mean of 0 and a standard deviation of 1. Okay, so now I also pointed out last time that when we're using the standard normal distribution, we usually use the letter Z to represent that distribution, whereas all the other cases are represented by an X. So we actually already did quite a few examples of how to calculate probabilities here. So for example, what if I have the standard normal distribution? And I want to know the probability that Z, the standard normal random variable, is, let's say, somewhere between 1 and 2. Now, just like with the uniform distribution, we're actually calculating an area under the curve. But the thing is, how do we actually come up with that? It was easier with the uniform distribution because it was just a rectangle. But now it's a lot more complicated. So we need to rely on our calculators. So you would go to second comma, I'm sorry, second vars. To get to that menu, hopefully you have one of these available today. Second vars, and that gives you a list of distributions. The one you want is number 2, normal CDF. All right. And then once you got there, you've got to give it 4 pieces of information. Lower, upper, the mean, and the standard deviation. So lower and upper refer to the fact that this is an interval between 1 and 2. All right. And then, of course, the mean and standard deviation are 0 and 1 because we are told that this is the standard normal distribution. All right. So if you pop those into your calculator, oh no, what happened there? Yeah, this is something new that they just started at Microsoft. They're trying to, I think this little symbol means I'm co-pilot and I want to help you here. And so I don't want it to help me here. So I'm going to try to ignore it. I have no idea what it would do anyway. It's it's almost like having Siri watch you all the time. So anyway, you put that in your calculator from 1 to 2. Again, the mean is 0. Now, by the way, I do want to point out here that the calculator, when you first open it up, you've never used it before, it assumes that you mean the standard normal. If you noticed when you started using this the other day, it already had 0 and 1 in it because that's the standard assumption. If it's not, then you have to change it yourself. All right, so you end, oh, okay, I obviously made a typo. Not a problem. All right, here we go. It's 0.1359. All right, so that means this area, it's 13.59% out of the grand total. Okay, in other words, 13.59% of the total is in here. So let's say this refers to the price of some good or other. There's a 13.59% chance that the price lands between 1 and 2, let's say. By the way, here's a little fun side note. You know how easy it is to make typos with these calculators. If you get the upper and the lower limits backwards, what'll happen is rather than giving you an error message, it'll give you the right probability, but it'll make it negative. So if you see a negative probability, check and see if you've gotten the lower and the upper backwards. If you forget about the mean and the standard deviation and leave the wrong ones in there, usually what ends up happening is the probability that comes out of it is either extremely tiny or extremely large. And that usually is a hint that something's not right. So for the most part, these are very straightforward. The only thing we have to be aware of is what to do about infinities. So if you had something like this, what's the probability that z is greater than or equal to 1.50? All right, so because you know the curve continues all the way out to positive and negative infinity, that implies that what we're actually looking for here is everything from 1.50 up to infinity. But you recall from last time we met on Tuesday that there is no infinity key, so you have to do it like this. And be careful, it has to be literally exactly what you're seeing here. Second, now the comma key is directly above the 7. And if you notice directly above it, in tiny little letters, it's sorry, it says EE, which means it's about to enter into scientific notation mode. That's really what we're doing here, because what this is saying to us is that this is being replaced with E99, which is shorthand for 1.0 times 10 to the 99th power. Okay, so in other words, it doesn't have infinity in it. It can't. It's a finite calculator, but it has a large number that will do the job for us. Sometimes we run into approximation issues, but it usually does a very good job. So you put that in there, and if it's negative infinity, you just do the same thing with a negative sign in front of it. And then, of course, these last two parts don't change. So if you do that, let's see what we get. Okay, lower at 1.5, upper is infinity as designated second comma 99. And that's going to be rounded to four places. Um, that's a lot smaller than okay, sorry, I have a typo here. All right, let me try it again. Here it is, 0.0668. Okay. Now, as you recall from last time too, we can take advantage of the symmetry of this distribution to conclude that on the left-hand side of the mean, we can go ahead and calculate this the normal way. And of course, remember here, you're going to put negative second comma 99, and it'll show in the window minus C99. But you don't even have to type it into your calculator because you already know from the principle of symmetry that it must be 0.0668. They have to equal each other. Okay. So in other words, if I bring them all together, now here's something else we can actually take away from this. What if I need to know this probability? Again, we could go to the calculator and let's do this just to get some practice. But it turns out we don't really need to do this either. All right, so if you go ahead and do that directly on the calculator, here's what you'll get. 0.8664. So why did we not need to do this directly with the calculator? Because it turns out, of course, the whole area equals 1. So that means that the area in the middle must be equal to one minus the probability of being in the right tail minus the probability of being in the left tail, 1 minus 0.0668 minus 0.0668. So when you do this now, it's possible that there'll be a slight difference due to rounding. Because remember, we are rounding these to four places, and the actual number of digits goes on quite a bit further than that. So, but yes, it does match up with 0.8664. So sometimes you can calculate these probabilities just by your knowledge of the properties of this normal distribution. Okay. And one more thing I want to review is just the idea that the center, as you know, is 0, or the mean. So the area above that has an area of a half, and so does the area below it. So that the area adds up to 1, and then in addition to that, the left and the right-hand side are exactly the same. All right, so I think that's as far as we got. Now, I think we had like maybe one example with the normal distribution when it wasn't the standard normal case. So we were using the case of an exam. Let's say, for example, the scores on an exam are normally distributed with a mean of 80. It's the same example we had the other day, and a standard deviation of 5. So when the problem gives you a normal distribution, either it has to tell you that it's the standard normal, or if not, you have to be told the mean and standard deviation. You can't figure that out for yourself. You have to be told that information. So we can calculate probabilities the same way with the calculator, but we have to be careful to change the mean and the standard deviation. So if I wanted to know, oh, let's say the probability that our score is, let's make up a new one. How about 70 or below? Okay. So X is the score. And remember, I did mention this before. Z is used for only the standard normal case. All the rest of them are used in those cases we use X. So that means I'd like to know if I take this test, what's the likelihood they'll get a 70 or less? Okay. So we got a second norm of ours. Number two, normal CDF. By the way, if you look at this menu, you notice there's also a normal PDF. Let me just mention this as an aside. Do not use it ever for any reason, okay? Um, it is not, we do not need it for this class. And let's just forget that it exists. Just always go automatically to number two, normal CDF. Okay. So if you were to accidentally choose this one, you would discover that it's asking you for information that you're not prepared to give it. In other words, it's asking you different questions, and that would give you a hint that you've chosen the wrong one. So just make sure you always use number two, normal CDF. All right, anyway, so you're going to tell it that the lower limit is negative infinity. Upper is 70. Now, here's the important detail here is this. Make sure that you remember to switch these. In other words, if you accidentally leave it at 801, of course you'll get a number that's way, way off. So, we're using a lot of examples with the same mean and standard deviation. So it's easy to forget that in some cases you have to switch the mean and the standard deviation. But you'll know right away, pretty much, if you forget about that part of it, like I said, you'll probably get a number which is really small, like 0.0000000, on and on and on, or else it'll be 0.9999999, that kind of thing. And that would be a hint to you that you've probably done something wrong. All right, so let's do this the right way. Minus infinity up to 70. Then don't forget to change the mean and the standard deviation to 80 and 5, and you should get 0.0227. All right, so notice the chances are pretty low. Now, the reason why it's so low is because if you were to rewrite that in terms of standard deviations, this is actually two standard deviations below the mean. Okay, that's pretty far off from the center. In the normal distribution, anything outside that range, two standard deviations away from the mean is quite distant. If you remember from the empirical rule, 95% of the area should be inside there. So that means that outside areas are going to be quite small. All right. Let's see. Now, here's where it gets interesting. What if I now ask for the probability of getting at least a 90? All right, so let's try that one. Remember, this is equal to second comma 99. Let's try this. Oh my God, does that look familiar? It does, because of course, oops, of our friend symmetry. This mu, this 90 is actually mu plus two standard deviations. So naturally enough, these two, this one is two below the mean, two standard deviations below the mean, this is two above. Or you can think of it in terms of the points on the exam. This is 10 points below, this is 10 above. Therefore, the two must be equal to each other thanks to symmetry. So just a little side note here. All right, so symmetry, remember that's our favorite property, symmetry. And so that's going to help us out here. All right, now there is a formula in here, which, by the way, I just want to point out, just as an aside here, it used to be common practice to use tables to come up with these probabilities. Mathematicians would have sat down and figured all these probabilities out for us, but only for the standard normal distribution. And they would have been put together in a table. In fact, I'm sure this book has that same table in the back somewhere. We don't need the tables because we have our calculators, but before these calculators came out, um, that was normally how it was done because the actual math going on behind the scenes is quite complicated. So there would have been tables in the back showing all the different possible probabilities for the standard normal. Now, that meant that you needed to do something different for every other case. Like for this one with the grades, there is no table for a mean of 80 and standard deviation of 5. There's just the one table and that's it. So what happens is, in order to use the table, there's a formula that lets us convert from any normal random variable to the standard normal. And it's a very straightforward formula. In fact, you may have seen this before. We actually used this earlier in the course when we were calculating z-scores. And this formula, very simple looking formula, tells us how to convert one to the other. So I put it there. It's really gigantic so that you don't forget about it. Um, and this is known as a z-score. And that z-score simply tells me how many standard deviations we are above or below the mean. And obviously the reason for the z is because it's based on the standard normal. Okay, so that's why you may have heard this term before. In fact, we asked about it on the first midterm, the z-score. And so in this case, remember, x is normal. X is the score on our exams. Mean is 80. Sigma is 5. So let's say we wanted to know the probability of getting a score between, let's say, 75 and 85. Now, you can go into your calculator and do this directly. In fact, let's do that right now. And then I'll show you an alternative way of doing this, which is a little bit more time consuming. Okay. Oops. Let me fix that a little bit. That's better. I want it to be as neat as possible. All right, so if you put those into your calculator, you should get Uh, 0.6827. Now, let's go back and revisit this formula. So this question could be rewritten as, so what I'm doing is converting each of these elements of my inequality to z-scores. Okay. And so now if you go into your calculator, you'll see something interesting. Let's try this. Why it's 0.6827. What a coincidence. No, it's not a coincidence. It's the same thing because it's the same information, only expressed through different units. We have actual points up here, and then down here, these are known as standard units. So it's the same probability because it represents the same thing. So if you were to draw the two graphs together, so up here on the top is X, which has a mean of 80, standard deviation of 5. And down here is your standard normal random variable. So 80 in the top is equivalent to 0 in the bottom. 85 is equivalent to 1 down here because that's one standard deviation above the mean. Then here, 75 is the same thing as mu minus sigma. It's down here, corresponds to mu minus sigma. Now, of course, the curves are not drawn perfectly, but it's the same thing. And like I've made this analogy before, it's no different than switching back and forth between Celsius and Fahrenheit. You're just changing the units. That's all. It's the same thing, except in different units. So anyway, so now we see how the two are related to each other and how to calculate probabilities. So now, what do we do next? Okay, so let's see if they have any more examples for us. The third and final probability distribution in this chapter, which is coming up next. Oh, by the way, we're going to save the Excel, like I said, for next time. We're definitely going to do it. It's awfully important, but I'd like it to wait till we're all together in the classroom at the same time. Okay, this can wait. Okay, but don't you worry, we're going to do it. So let's see, what do we have here? Ooh, all right. So let's do this example they're giving us here. We have this tire company. They want to know how many miles the tires will last. Okay. So let's assume that the mean mileage is 36,500 per tire. So X is the mileage of a tire. How far can it go before you need a new one, in other words? And then X is normal. And once I tell you that, you notice it's clearly not the standard normal because the mean is 36,500 And the standard deviation is 5,000. They'd like to know the probability that a given tire that they've chosen at random is more than 40,000 miles. Okay. Well, you know what? We know how to do this. It's easy. It's a breeze. What you're going to do is, of course, go back to second vars, uh, number two. Now, lower would be 40,000. Upper is positive infinity. U is 36,500. And sigma is 5,000. Okay. So if you plug those in, let's see what you get. So don't forget to change, by the way, the mean and the standard deviation. Otherwise, disaster will result. It's point, I'm getting rounded to four places, 0.2420, approximately. All right, so remember the mean is 36,500. So this is what we're looking for. And we just discovered that it's 0.24. And that's all there is to it. It's so straightforward. All right, now you're saying, oh, come on. Oh, by the way, they went ahead and computed the number of standard deviations. In this day and age, that's not absolutely necessary because we have the calculators, but you never know when MindTap might ask you to do that. So let's do that anyway. I wouldn't be surprised. They'll probably require you to do this. It's going to be a while before you have to do this in MindTap, but it's going to sometime in early April. You'll be happy that you learned about this. So for this case, 40,000 minus 36,500 is, let's confirm this, 36,500 divided by 5,000, it's 0.7. So that tells me that the probability that X is greater than or equal to 40,000 is the same thing as the probability that Z is greater than or equal to 0.7. And you can confirm that in your calculator if you want to. It's not really necessary, but they are the same thing. So I'll note that up here, mu plus 0.7 sigma. All right. So now we're getting to a point where we're getting awfully good at calculating normal probabilities. And that's good because we're going to need them constantly throughout the rest of this course and the fall. Okay. This will be your constant companion, by the way, for the rest of your statistical career. And here, by the way, they're showing you a picture of the table. If this was like a while in the past when there were no calculators, this is how you would have looked up your probability. Now, sometimes in high schools, when they start to introduce you to statistics, they may use the tables as well, but I think you'll find that it's easier to just use the calculators. All right, let's see. Oh, well, now they're getting into some deep waters. They've decided to go ahead and give people a guarantee of some kind. Okay. So what they want to know is what is the value of X? such that the area greater than that is 10%. So in other words, imagine them saying, listen, we're going to give out some kind of a guarantee here, where if your tire doesn't last a certain number of miles, you'll get a refund. But they don't want to be constantly giving people refunds. So they've decided to figure out where they should set the guarantee to make sure that no more than 10% of the customers are able to take advantage of it. So they're doing something a little different here. Um, what they're saying is, given this information, there's some number of miles such that the area in the right tail is 10%. So that's what we're looking for. Now, you're probably saying, what are we supposed to do with this one? That's a very good question. Now, the calculator can help you with this, but we have to make a little change here first. What we're going to do is first calculate this in terms of the standard normal distribution. Oh, actually, you know what? I just realized I've drawn this incorrectly. They want to know, I've got it in the right tail. It should be down here. Yeah, that's right. It's got to be down here because they're looking for no, people are not going to ask for a refund unless they get too few miles, not too many, too few. So the question is, at what cutoff point will no more than 10% of the people be eligible for a discount or actually a refund? So it's going to be down here on the left-hand side. All right. So what we need to do is figure out where this is with respect to the standard normal. So what we have to do is this. Let's draw this in terms of standard normal. And so you can see the means are the same here. I'm looking for the corresponding location under the standard normal. So what I'm looking for here is X standard deviations below the mean. Now, it turns out that there's a special command in the calculator that will do it for us. Okay, so this is, I'm opening up another treasure chest for you here. When you see this command, you'll say, wow, that's powerful. So think of this, normally what we would be given is a location under the curve and we'd be asked for a probability. Now it's the other way around. We're being given a probability and we're being asked for a location, meaning a number of standard deviations away from the mean. So we're doing the inverse of what we were doing earlier. And so therefore, the name of this command will make sense to you when you see it. Let's see. All right, what is this mystery command? I shall move it down here. You go back to your second vars menu. Okay, but this time we're going to choose number 3, INV norm, which means inverse of the normal distribution. Okay, now once we've done that, it's going to ask you for an area. Now the area means in this case the left tail. Now here's where we have to be careful. Everyone may have a slightly different calculator. So on the one I have, this TI-84 plus CE, this is what I'm seeing. For the tail command, you have to choose between left, center, and right. Now, if your calculator does not show the tail command, it is assuming that you mean left. So what I want us all to do is, if yours does show the tail command, move it to left so that we're all doing the same thing. I'll just slide it over. Actually, I don't think you can do this until you filled in the other information first. But when we get to the bottom, um, we're going to all change it to the left tail. So that way, no matter what calculator you're using, we're all doing the same thing. So the area then is the area in the left tail, which is 10%. The mean and standard deviation are 0 and 1. And then when you type in all these numbers, you'll get negative 1.28. Now, what in the world does that mean? That means that this x is negative 1.28 standard or 1.28 standard deviations below the mean. And how does that help us? That's a good question. Because we don't care about standard deviations, we need to know mileage. But we know this formula, so all we have to do is plug numbers into this formula. And that'll give us what we're looking for. Okay. So it's 36,500 minus the product of 1.28 and 5,000. 30,010. Not 10, 100. So in other words, we're going to guarantee the customers, if your tires don't last at least 30,100 miles, we'll give you a refund or new tires, whatever, probably new tires. They won't give you your money back, but they'll give you new tires. So in other words, that means that under this normal curve, this is mean. Oh yeah. Okay. Wow, now that seemed very complicated and confusing. They wanted us to see the connection with the standard normal. Now, it turns out that even this much work wasn't really absolutely necessary. Now I'm going to show you how to do it directly. Okay, in other words, we'll start here. And I can very conveniently, this is something I can't do on the whiteboard, on the blackboard, I mean. I can just copy and paste. What if we decided to do this without figuring out how many standard deviations we are? Now, be aware that in the Mind tab, they may ask you for this 1.28 standard deviations, but if they just want the mileage, you can do this instead. Okay, now remember, with this X, the mean is 36,500. Standard deviation is 5,000. So if, let's say the question says, how many standard deviations below the mean will we be, or do we want to be for this guarantee? And that would be, the answer would be 1.28. But if they want to know the number of miles, then that's it. That's all they need to know. Then you can do it like this. Second vars, number 3, INP norm. And now this time, we're going to do it a little differently. The area is still 0.10. Don't worry about that. And by the way, make sure you're on left. Okay, remember up here at the very bottom, make sure it says left if you have that option. If you don't have that option, don't worry about it because it's already defaulting to left. So, by the way, we're gonna, after spring break is over, it will have been quite a while since you saw this material. We'll definitely go back and revisit this and get some more practice with it. I certainly don't expect you to remember all this stuff for another week and a half without reviewing it. So we'll do this again. Okay. But it's good to get it a first look at it because then this way, when you see it again, it'll make a lot more sense, in my opinion. Okay. So here's what you're going to do. Now, what's different this time is that instead of the mean of zero and standard deviation of one, we'll use the actual numbers for X. Okay. And now there is a slight rounding difference here. The reason why this happened is because 1.28 is not exactly correct. Okay. It's like 1.281 something something. So by doing it this way, though, we're getting a more precise result. So it's actually 30,092. So I guess the mind tab will have to figure out how much leeway to give you when there's rounding differences. But you can see here we went directly to X without needing to go through the standard normal distribution. Okay. So probably this will be the way to go. But again, it'll depend on the question. Okay. Wow, this is a lot of material for a Friday morning just before spring break. But like I said, don't worry, we'll review this again. And we'll do this in Excel too. Don't forget. Yeah. So when we get back, we're going to review it because if we're going to go back and redo it in Excel, we have to review it anyway. So we'll be all set. Now, in the meantime, I think we have a few minutes here. Let's at least introduce the so-called exponential distribution. This is the third of our three um, continuous distributions. Now, this one is a little different from the others. I mean, they're all different. They all have different purposes. So this one is actually related to the Poisson. Now, if you remember, um, Poisson distribution can be used to determine the probability of a given number of events occurring during a given time interval. Assume that on average, um, let's say we notice that 8 customers enter a store every hour. Okay, and so in other words, if you've noticed that on average 8 customers come into your store every hour, and then you might ask the following question: what is the probability that over the next hour there'll be 10 customers, or 3, or 7? That's a job for the Poisson, but um, this probabilities can be determined the number of customers entering the store during the next hour using the Poisson distribution. But now here's where we can flip this around. Suppose instead that we want to compute the probability or probabilities for the time until the next customer arrives. That's a little bit different. Saying, for example, what's the probability that it will be 30 minutes before the next customer shows up? So for that, this type of probability can be answered or computed using the exponential distribution. Now, here's a bit of sad news for you. The exponential distribution is not in your calculator. If you scan through that list of probability distributions, you won't find it. It's not there. So we have to do it ourselves, either using Excel or else we have to actually use the formula. Okay? In other words, we have to algebraically implement the formula. Now, the formula is not really all that horribly difficult. Well, here it is. It doesn't look too terrible. And again, there's our old friend E. Oh my God. So the formula for computing exponential probabilities is, now you recognize a couple of old friends here. Um, just move this down here for a minute. Okay, so let's say, for example, mu. So in the last case, we were told that, what was it, 10 customers per hour? Eight, sorry, it was eight. Okay. If on average, then mu equals eight. It's that simple. Remember, this is exactly how it worked for the Poisson. So you can see the tie-in with the Poisson distribution. And then that just leaves us with E. E is, a constant. It's approximately equal to 2.71828. We saw this also in the Poisson distribution. So now keep in mind, since this is a continuous distribution, we can only compute probabilities or intervals, not individual values. So, for example, we could compute probability that the next customer arrives between 10 and 15 minutes from now. But the probability of arriving at a specific time, such as 15 minutes from now, is defined to equal zero. So we only are interested in intervals. So in other words, I might want to say, well, given that eight customers come in the store every hour, what's the probability that it'll be between 10 and 15 minutes before the next customer? You can easily imagine why that might be handy. Imagine you're working the store by yourself one day and you have to make an important phone call, which will only take a couple of minutes. So there's nobody in the store and you look around and say, oh my God, how much time do I have before somebody else comes in the door? So then you can see why this kind of thing might be very helpful. So also for the exponential, if you notice, it does not allow for negative values because we're looking into the future. We're looking at times in the future. But the probability itself, I mean, you can see it's not a terribly difficult formula. So if I wanted to know, let's say in this case, mu is 8. Oh, one more thing. Now, here's where we have to watch it. That 8 is an 8 per hour. If I'm asking about 10 to 15 minutes, I'm going to have to convert these into fractions of an hour. Okay. So I'll tell you what, I didn't realize it was so late. I think that maybe it would be best if we save the rest of this for when we get back, because this is a fairly complicated problem. And we still need to go back and revisit all the Excel commands for the normal distribution. So I think we got a lot done today. Oh my God. You really zoomed through this material. So when we're done, I'm going to be posting this set of notes onto Blackboard, so you can read through it at your leisure. There will also be a recording available both on Blackboard and on my YouTube account. I mentioned that once before. The reason for doing that is so that sometimes, like Blackboard itself, these videos swallow up an awful lot of time. And so I find that, man, there's some fun stuff up here today. It's often easier for me to do both. Okay. So in other words, if you come back over here, this is my account over here. Let's see, where does this have my information? There we are, Dr. ACA. So if you look at my channel, it's called, there it is, there it is. You'll notice that, oh my God, there's all kinds of notes in here from all over. Look at all these notes I've produced over the last few years. So I've created a separate playlist just for us. And that is, God, where is it? Maybe not. Well, I'll tell you what, if it isn't there, I'll create one for us. And that way, if you want to, you can go find it in here instead of looking in Blackboard. So, plus, by the way, these are all publicly available. So, for some reason, you decided that you want to read one of my other, look at some of these other notes. They're all right here. God, look at them all. All right. Anyway, so we'll stop it right here, and then I'll see you a week from Tuesday. And I hope you have a great spring break. All right. So, bye, everyone.